Welcome to another fun-filled edition of Comet Algebra. This video is for Algebra 1, Chapter 8, Section 5, Exponential Functions. Now, we've used linear functions to model many real-life situations, but exponential functions are very useful too, representing other scientific and financial models. In linear, the change is constant. It goes up the same each time. However, in exponential, the growth starts out kind of slow and then speeds up very, very quickly. And we looked at that in class at the graph when we compared a linear to an exponential graph. In the same way, a linear equation, we learned y equals mx plus b, where m is the slope and b is the y-intercept. Well, exponential functions are written in the form y, or like I wrote here in function notation, f of x, y equals a times b to the x. And in exponential, the a this time is the y-intercept. I don't know why they do that. They just change it up on us. So a is the y-intercept and b is the growth. Now this word growth, we'll have to really discuss it in class because exponential functions can be increasing or decreasing. So b, the growth, is always positive, and it's not equal to 1 because if it were equal to be 1, it wouldn't be increasing or decreasing and it wouldn't be exponential. So we'll have to discuss growth, how if it's positive all the time, well then how can the graph be going down? So it's a question I want you to think about. Like this is an exponential graph where it's going up. Okay, so that could be a growth of 2 or 3 or 4. But we also have exponential functions that start up here and come down. But how can that be if I just told you that the growth is always positive? So that's what I want you to think about. Now, both of these exponential graphs that I drew, they approach a line that they don't cross. This one, for instance, it's going to keep getting steeper and steeper and steeper, and it's never going to cross this blue line. I'll try to extend it a little further. These graphs aren't fabulous, so we'll be looking at this a little more. So it's going to get closer and closer. This one is going to keep decreasing, and it's going to get closer and closer and closer to this x-axis, but it's never going to cross it. So these lines that the graph approaches but never crosses are called asymptote lines. And this, we'll discuss this more in class, and this is kind of getting into a real advanced algebra and calculus topic. But for now, I just want you to be familiar with the term. All right, so let's take a look at some of these exponential functions. So we're going to graph y equals 2 to the x. Now, we could enter it in our calculator, or we could do it old school by doing a t-chart. So that's what I'm going to do. So as I enter -2 here, I'll just do the math over here on the side. So I have 2 to the -2 power, which we know we flip. Negative exponent, we flip it down here, and that becomes 1/4. Okay, this 2 to the -1 power is 1/2. Anything to the 0 power is 1. 2 to the first power is 2. 2 squared is 4. 2 to the third is 8. So now I'll graph these points over here. So now that I've plotted the points, I will connect them the best I can with my stylus here. Okay, that's not horrible. So you can see as it's going in the negative direction, it's going to get closer and closer and closer to this x-axis, but it's never going to hit. And so that is an asymptote line for this graph. And it's just going to keep on getting bigger here as it just keeps doubling. All right, next one we're going to graph is y equals 1/2 to the x power. So let's do the math over here together. So we have 1/2 to the -3 power. And remember, we have to flip this so it becomes 2 to the third power, and that is 8. Now we have 1/2 to the negative 2 power. Remember, with the negative exponent, it flips to become 2 to the second power, which is 4. And then we have 1/2 to the negative 1 power, which is 2. Anything to the 0 power is 1. 1/2 to the 1 power is 1/2. And 1/2 squared is 1/4. So now I'm going to graph these points. And now that I've graphed the points, I'm going to do my best to connect them. Okay, I got a little close to the x-axis there a little too soon, but you get the idea. So now remember what I asked you about how can an exponential be decreasing if the growth is always bigger than 0? In other words, we can never have a negative slope. Well, this one pretty much looks like a negative slope, but look, this is not negative. And so if we compare that to example 1 here, where our growth was 2, so again, they're both positive, but when the growth was 2, it's increasing. When the growth is 1/2, it's decreasing. So I want you to take a note of that. The growth in exponentials is never negative. However, it can be decreasing if the growth is a fraction. Now for example 3, we are asked to take this equation back up to the same graph in example 1, and we'll graph this on the same set of xy axes. All right, so I took the example 3 equation and wrote it up here. Y equals 3 times 2 to the x. And then I just put another extension on my t-chart here for those values. So really what we're doing is taking 3 times these values that we already did, 2 to the x. So 3 times 1/4 is 3/4. 3 times 1/2 is 3/2. We put a 0 in, we get 1. 1 times 3 is 3. Times 3 is 6. And I'm not going to have enough room on my graph, but we will graph the ones we can. So I'm going to take these now and put these points over here on the xy axis. All right, I fixed my mistake right here. That was supposed to be 3/2. And then I plotted these points in blue, and now I'm going to do my best to connect them. And you can see that we do have the same shape here, but what this 3 did, it just moved the whole thing up a little bit. So that's example 3. We're going to do more of this in section 6, but let's just get a little started with how we're going to use this in word problems. Yes, we wrote above this that it's a times b to the x, where a is the intercept and b is the growth. So what I did here, instead of writing a and b, I just put it in words. I like to say y equals start times growth to the x. And this helps us with word problems because if we can figure out what number in the word problem is the start and what number in the word problem is the growth, we can plug that into the right place. So example 4 says, under ideal conditions, bacteria in a petri dish double, that's a very important word there, double every hour. If you start with 40 bacteria, how many will be in the dish after 8 hours? Well, double, that is telling us the growth. So we have a growth factor of 2. This 40 bacteria is how many we're starting with. So we can write our equation. Y is the number of bacteria. We're starting with 40. It's doubling, so that's my growth. And x is the hours that go by. So that's my general equation. And in this particular problem, they want to know after 8 hours has gone by. So if we punch this into our calculator knows PEMDAS, and it will do 2 to the 8th power and then multiply it by 40. So if I punch this correctly on the calculator, I got 10,240 bacteria after the 8 hours. Okay, that's a lot. So you can see how quickly exponential growth happens. This is so different than if it's just increasing by 2 each time. All right, so now you have the knowledge you need for section 8.5. So have fun with math.